And in the last part of the lecture, we are going to see some applications of differential equations and how can real-world problems be translated into differential equations. Well, the first very kind of reasonable scenario is exponential change, right? Well, I will give you an example. So imagine a situation in which we have some population, I don't know, humans, bacteria, whatever, and the resources are unlimited, right? So imagine that uh, at the moment, so that there is so much space to grow that we can just assume that the resources are unlimited. And in this case, if t is time and y is population as a function of time, um, in that case, the rate of change of population is going to be proportional to population itself, right? So I mean, but basically, the rate of change is proportional. I mean, if there's humans, then the rate of change of population is proportional to the number of babies grown, born in some period, minus the number of deaths. And of course, if the population is, I don't know, increased twice, then that number is also going to be increased twice, right? So generally speaking, the rate of change of population is proportional to the population. So the differential equation that describes it is just y prime equals ky, where k is some positive constant. Now, let me solve this equation, right? So this equation is linear, and I can move ky to the left-hand side, y prime minus ky equals 0. And in order to solve it, I need to find the integrating factor, right? So the integrating factor, so the first thing to do to find the integrating factor is to look at the dsp. So the dsp is just minus k. So the first thing is to integrate minus k with respect to, so here the independent variable is t, right? So minus k dt. And this is going to be just, of course, minus kt. So the integrating factor is e raised to this power. So the integrating factor I of t is e raised to the power minus kt. So now multiplying by e to the minus kt, I will get y prime e to the minus, sorry, e to the minus kt minus k y e to the minus kt is 0. Now, the left-hand side of this expression is, in fact, we know it from the theory that it is y times e to the minus kt prime is 0. It is the derivative of the product of the integrating factor and the unknown function. Right? So now, if the derivative of something is 0, it means that something is just constant. So y times e to the minus kt is a constant. Solving for y, we get y equals c times e to the minus kt. And this is the answer, right? So if we want to model the population whose rate of change is proportional to the population itself, then this is how we can solve the differential equation. Now, so basically, that's the idea. So the equation is dy dk equals ky. And so notice that this equation is linear and separable at the same time. So I have just solved it as a linear equation. So I have applied the method of integrating factors to solve it, and it works. Now, here is a different example. Essentially, it is the same differential equation. So if you have a radioactive material, then basically the rate at which it changes is also proportional to the amount of material, but now the coefficient of proportionality is negative, right? So because it is exponential decay rather than the exponential growth, right? And basically it is described by the same equation, only now the coefficient in front of y is negative. Now, and again, of course, this differential equation is linear and separable at the same time. So let me just to show you how we can do it using the method for separable differential equations instead. So you can solve it both as a linear, which is by integrating factor, or as a separable, which is by separating the variables and integrating. So let me do it as a separable, right? So separating the variables and integrating, I'm going to move dt to the left hand side and y to the, sorry, dt to the right hand side and y to the left hand side. So doing that, I will get dy over y equals minus k dt. So this is the separation of variables. Then I'm going to integrate. So integrating this, I get a ln of absolute value of y on the left and minus kt plus constant on the right. Now, so here we have kind of a problem that we have ln of absolute value of y, and basically it can be either ln y if y is positive, or it can be ln of minus y if y is negative. And this, I mean, if you just want to solve this differential equation, it kind of poses a problem. So it leads to unnecessary complications. So which is why, in my opinion, it is in fact easier to solve this differential equation as a linear, so which is by integrating factors, rather than as a separable, which is by separation of variables. But if we are going to be interested in just a radioactive material, so then the amount of radioactive material cannot be negative, right? So if y is the mass of radioactive material, then there is no such thing as negative mass. So which means that we can just assume that y is positive, and in that case, we get that ln y is minus kt plus constant, and then applying the exponential function, we get e to the ln y is e to the minus kt plus constant, right? And which leads us to e to the ln y is just y, so it is y equals e to some constant times e to the minus kt. Well, and basically this e to the c is just again some other constant, and that constant is positive. So you can in fact even compute it in terms of, I mean, if you assume that y, that there is some initial amount of radioactive material, so y of 0 equals y0, then you can substitute that as t and y to this equation. So then doing that, you will get y0 equals e to the c times e to the 0, so which gives you the relation e to the c equals y0, right? So the final answer is y equals y0 times e to the minus kt. Okay, so my point being is that you can also solve this differential equation as separable, but it's kind of a bit harder than doing it as a linear. So which is why in practice, if your differential equation is linear and separable at the same time, then I would always do it by integrating factors rather than by separating variables. But anyway, so that was the second equation about radioactivity, and here is my third example, and it is fairly more complicated, so I will try to explain it. I mean, you can just pause the video and read, but let me explain what's going on here. So here we have a tank. So there is like a tank, and there is a mixture, some brine, so which is water with salt inside it, right? So initially, there is 380 liters of this mixture in the tank, and the initial amount of salt is 220 grams, right? Now, there is an inflow, so there is probably like, I don't know, so imagine like a tap here. Okay, I'm a poor drawer, sorry, so I guess I'll just use arrows. So there is an inflow of brine with salt. So, and the inflow contains basically 2 grams of salt per liter, and it goes in at the rate of 20 liters per minute. Okay, so at the same time, there is the outflow. So you can imagine some kind of a sink here. I don't know, some kind of sink, and there's another pipe. Okay, and there is the outflow at the rate of 15 liters per minute. Now, inside the tank, the brine is being constantly mixed, right? So we can assume that the salt is distributed uniformly over this mixture, right? Now, so we need to determine the amount of salt in the tank 25 minutes after the process starts. Now, why is this a differential equation? This is because if we let y of t denote the mass of salt, right? So this is the mass of salt in grams, where t is measured is time, measured in minutes. Then basically this inflow and outflow, they provide us the rate of change of the mass of salt, right? So now the derivative of the mass of salt, y prime, is the rate of change. And the rate of change is made out of two terms, basically, the flow in and the flow out, right? So let me just try in minus out, right? So the rate of change of the amount of salt is basically there is some salt flowing in minus some salt that is flowing out, essentially. Sorry. Okay, now, what is the inflow of salt? So the inflow of salt is made out of the concentration of salt in the inflow, which is 2 grams per liter, times the flow itself, right? So which is 20 liters per minute. And this is just 40, and notice that liters cancel out, grams per minute. Which makes perfect sense because, if mass of salt is measured in gram, then the rate of change is going to be measured in grams per minute. So it makes sense. All right, cool. Now, the outflow is a bit more complicated, but the idea is the same. So it is going to be the concentration of salt times the strength of the flow, right? So it is going to be the concentration of salt, and the concentration of salt is actually the mass of salt divided by the volume of salt. Well, times the outflow, and the outflow, we know it is 15 liters per minute. Okay, now what is the mass of salt? Well, the mass of salt is, in fact, we have a notation for that. It is just y. Now, what is the volume? Now, so notice that the initial volume of the brine is 380 liters, but it is in fact changing. So let me write it here. So volume. So initially it was 380 liters, but it is not staying constant because the inflow is 20 liters per minute and the outflow is 15 liters per minute, right? So which means that the volume is actually growing because the volume that comes in is bigger than the volume that goes out, right? And it is growing at the rate of 20 minus 15, so which is 5 liters per minute, right? So it means that if the volume is growing at the rate of 5 liters per minute, it means that the volume t minutes after the beginning of the process is going to be 380 plus 5t, right? So imagine that if t is 1, then there's 5 more liters. If t is 2, then there's 10 more liters than initially, and so on. So in particular, 25 minutes after the process starts, so we are going to have 380 plus 5 times 25 liters of the mixture. Okay, right? So this is the volume. So volume is 380 plus 5. All right. And putting it together, we will get the following. So y prime equals the flow in is 40 minus the flow out is y divided by 380 plus 5t. Well, there should be 5t, of course. Times 15. So times 15. And this is the differential equation that describes that governs the process of mixing the liquids. So notice that we haven't used one condition here. So the fact that initially we have 220 to 20 grams means that y of 0 is 220. Okay. And by the way, just to make sure that the dimensions match, so y is measured in grams, right? And the volume is measured in liters, right? So this is the concentration in the outflow is measured in grams over liters, which makes perfect sense. So it is consistent because now liters will cancel out, and the outflow is also measured in grams per minute. All right. So again, so this is the same logic explained in printed slides. So let me now just continue with solving this equation, right? Okay, so one thing that I'm going to do first, so I'm going to cancel by 5, right? So 15, yeah. So canceling by 5, I will get 3 here. 380 divided by 5 is 76. And this is 5, right? So I have divided both numerator and denominator of the fraction by 5. Right, so my differential equation now becomes y prime equals so let me at the same time move this to the left hand side because it is a linear differential equation. So usually we move the term with y to the left hand side. So it's going to be y prime plus 3y divided by 380 plus t, y equals 40. Well, and again, so y of 0 is 220. So this is the initial condition. Okay, the first step is to find the integrating factor, right? So the integrating factor, to find the integrating factor, I need to integrate the coefficient at y. So the integral of 3 over t plus 380. Sorry, not 380, of course it is 76. Yeah, sorry about that. 76 dt is going to be just 3 times logarithm of absolute value of t plus 76. Now, notice that we are interested in predicting what's going to happen in the future, right? So initially t is 0, but then we don't really care about what kind of what led to the process, right? So, and we are only interested in what's going to happen in future. So when t is non-negative. So and if t is non-negative, then t plus 76 is of course also non-negative, right? So we don't need the absolute value sign here. All right, so the integrating factor is really e raised to this power 3 ln t plus 76, which is e raised to the power ln of t plus 76 cubed, which is t plus 76 cubed. Right, so this is the integrating factor. And we know that if we multiply our differential equation by the integrating factor, then the left-hand side becomes the product of the derivative of the unknown function and the integrating factor. So y times t plus 76 cubed prime. And the right-hand side, well, is just 40 times the integrating factor. Times t plus 76 cubed. Okay. Now, taking the antiderivative, we get y equals, sorry, let me do it like this. So y times, step by step, t plus 76 cubed should be the antiderivative of 40 times t plus 76 cubed dt, which is, what is it? The antiderivative of t plus 76 cubed is t plus 76, so 40 times t plus 76 to the power 4 over 4. So 40 over 4 cancels out. So this is just 10 times this. Okay, plus constant. The initial condition allows us to find a constant, right? So letting y to be 220, and t be 0, 76 cube, I will get 10 times 76 to the 4 plus constant. So my constant is in fact 220 times 76 cube minus 10 times 76 to the 4, which is, I guess I will just simplify it a little bit, so minus 540 times 76 cube. Let me check my, okay, yeah. So which allows me to solve for y now. So let me erase this. Now, so let me just copy it over again. So this is 10 times t plus 76 to the power 4 minus 540 times 76 cubed. So this is my constant. Well, and finally I need to solve for y. So to solve for y, I need to divide by t plus 76 cube, or multiply by 1 over t plus 76 cube. So doing that, I will get y equals 10 times t plus 76 minus 540 times 76 cube over t plus 76 cube, right? So this is my y, and the final question was to find out how much salt is going to be in the tank after 25 minutes. So in other words, the question is to find y evaluated when t equals 25. So and that's basically it, right? So I need to substitute 25 for t, and this is going to be 10 times 25 plus 76 is 101 minus 540 times 76 cube divided by 101 cube, I guess. So that's just some number, and apparently it is approximately equal to 780 grams. I haven't checked it, but I think it's correct. All right, so this is how we do how we can solve a linear equation that arises from a mixture problem. Okay, and that's basically the end of the